Hi, welcome to another session of Circuits and Networks. In today's class, that is in class 2, under transient analysis, we'll look into the problems involved with initial conditions of inductor and capacitor when they are connected in series. So in class 3, we'll be seeing the same initial conditions of inductor and capacitor in parallel arrangement, and later on the combination of inductor and capacitor in series or parallel with resistor connected to supply and the switching action which takes place. That is what we are going to see in our future classes. So in today's class we will involve with RL circuit for switching action, RC circuit for switching action, and RLC, the combined circuits under switching action for series network. So what we have learned from our first class of transient analysis, whether the element is inductor or capacitor, what we need to remember that as soon as the switch is closed, when the inductor and capacitors are uncharged, then inductor immediately at the switch is closed, it behaves as open circuit, and capacitor it behaves as short circuit. So this is for switching when it is closed and both the elements are uncharged. And what happens to this inductor under open circuit? It behaves like this. So this inductor it becomes open circuit like this. Whereas for final conditions, that is steady state conditions, the inductor behaves as short circuit. So this uncharged inductor at the time of switching, when the switch is closed at t equal to 0, when behaves as open circuit. So the same inductor after charge for certain duration of time, that is we are taking the t is equal to some finite or infinite time. So the inductor behaves as short circuit. When you consider the capacitor at the time of switching at t equal to 0 plus, that is as soon as the switch is closed, when the capacitor is uncharged, it behaves as short circuit, and for a long duration of time it behaves as open circuit. Now this is quite different when you take the charged inductor and charged capacitor. For instance, you have charged inductor. When you have charged inductor, the same open circuit of this inductor will be having current source. Means what, the inductor is charged and it is acting as a current source at t equal to 0 plus. That is when the charged inductor is closed. When the charged inductor is closed, the behavior of inductor, it is taken in terms of a current source. When you have the same steady state conditions, the current source, you can see it is parallelly shorted. At the time of application, we are going to see this particular example. Now, the same condition with charged capacitor. It behaves as voltage source. The charged capacitor behaves as voltage source at t equal to 0 plus condition. And for the steady state condition, the voltage source is in series with open circuit. Unlike the case of charged inductor, where you have current source shorted with a wire, you have a voltage source which is open circuit with a wire. So this is the basic which you need to understand before going for transient analysis. So let us go with the problem. Now you can see in this network where you have 12 volts, you have 3 ohms and 2 henries. So there is a transient current I of t is flowing. The switch is about to closed. So the switching condition is shown as on and off. So right now the switch is off. The switch is on. So it is stated that in this circuit, the switch is closed at t equal to 0. So at t equal to 0, the switch is assumed to be at closed. With 0 initial conditions means what? The inductor's behavior. With 0's initial conditions, we need to find what is I, what is the differentiation of this current, and what is the acceleration of this current at t equal to 0 plus. So this mathematical differentiation can be termed as the velocity of current as well as the acceleration of the current, where I is the current flowing. So you can make the flow of charge which is equal into the flow of current. So the flow of current in terms of velocity and in terms of acceleration at t equal to 0 plus, we need to find out the values for these different varieties of currents. So how do we do that? So when the switch is open, that is, we are treating the switch is open condition as t equal to 0 minus. There is no current passing through the circuit. Naturally, since the circuit is not closed, no current is flowing through 3 ohms as well as 2 henries. So I of 0 minus, we are treating it is equal to 0. And what is the property of inductor? Since current through inductor cannot change instantaneously, naturally, immediately after switching, that is at I equal to 0 plus also, the value of current, the inductor will be 0. So these are two important conditions for inductor behavior. That is, the current through the inductor cannot change instantaneously. So I of 0 minus, which is equal to 0, will give you the same value of current as I of 0 plus. So these two are important points we need to remember for inductor behavior. Now as soon as the switch is closed, inductor acts as open circuit. This we have seen from the tabular column. So this circuit changes to this. So you can see here I have closed the switch. The switch is closed. It has the nothing impact on 3 ohm resistor, whereas the inductor it behaves as open circuit initially. As the switch is closed, the inductor behaves as open circuit. So since it is an open circuit, that is why I of 0 plus is also equal to 0. Because it's an open circuit, no current flows through the open circuit wire. So when there is no current flowing, so I of 0 plus is also 0. So here the theoretical condition of inductor as well as the practical uh, circuit gives us the same result. So I hope you understood this point. Now let us study the actual behavior of the circuit. So for the actual behavior of the circuit, that is for t greater than 0. So we are going from t minus, t plus, we are going greater than 0 conditions. Just after the switch is closed, when all the parameters are connected to the supply, this is how the circuit looks like. So 12 volts, switch is closed, it is connected to 3 ohms and 2 henries, and current I of 3 it is flowing. Now this current is known as the transient current, which is flowing through these two passive elements. Okay. Now I am applying the KVL, that is the algebraic sum of the voltage drop in a closed circuit is equal to 0. Minus 12, it is a given voltage source. 3I is the value of drop across 3 ohms. So it is also a voltage 3 into I according to Ohm's law. 3 is the resistor, I is the current. So resistor multiplied with current will give you the value of voltage. So plus 3I plus 2 di by dt. How we got this formula? According to the Faraday's law of electromagnetic induction, the voltage developed across inductor will be given as L di by dt. So L value is 2, di by dt is equal to 0. Hence we have satisfied the Kirchhoff's voltage law for this passive elements which are connected to 12 volts. So this is what we have obtained. So rearranging this equation 1, I am going to get di by dt. Just I have taken 2 and I have divided by 12 and 3. So 3 divided by 2 will give you as 1.5 I, and this is minus 12 here. So it goes to the right hand side. It becomes plus 12, but divided by 2 it becomes 6. So this we are reading as equation 2. I hope you understood this particular differentiation equation. Now at t equal to 0 plus, we need to find out the values. So in the same equation, I am substituting of t equal to 0 plus wherever I have I. So I of 0 plus by dt, which is equal to, now this is 6 minus 1.5 times I of 0 plus. I hope you understood this equation. We have derived from equation 2 this equation. Now this will give you the answer as 6 amperes per second, because this value I of 0 plus is 0. So 0 multiplied with 1.5 is 0. Therefore I have the value of di of 0 plus by dt is equal to 6 amperes per second. Is this clear? Right. Now differentiating equation 2 with respect to t, we get d square I by dt square plus 1.5 di by dt, and the differentiation of constant is 0, and we require the value of d square I of 0 plus by dt square. So at t equal to 0 plus, I'm just substituting the values of these things. So you can see here d square I of 0 plus by dt square plus 1.5 d times of I of 0 plus by dt is equal to 0. So this will give you the value as d square I of 0 plus by dt square is equal to minus 1.5 times d of I of 0 plus by dt, whose value is 6 amperes. So minus 1.5 into 6 will give you the value as minus 9 amperes per second square. So this is how we solve the transient circuit under RL when it is switched across 12 volts. Let us go with another example. Now instead of inductor, I have taken capacitor whose value is 10 millifarads. Milli indicates 10 to the power of minus 3. You have 12 ohms here. 28 volts is the supply and the switch is about to close. So the switch is open at t equal to 0 conditions. The switch is closed. Before that the switch is open. So we need to find out again the current di by dt, d square I by dt square at t equal to 0 plus. So we are dealing with the initial conditions. That is why we are finding out the current in terms of its velocity and acceleration. So it's a capacitor circuit. So when the switch is open, that is at t equal to 0 minus, there is no current passing through the network and capacitor is uncharged. Naturally, the capacitor is uncharged. So I of 0 minus is 0, V of 0 minus is 0. What is V of 0 minus? The voltage developed across capacitor. Notice I of 0 minus, the current through this entire circuit. So both the values are zeros because the circuit is not connected to 20 volts before the switch is not closed at t equal to 0. At this condition, we have equation 1, equation 2. Now, since the voltage across capacitor cannot change instantaneously, like in the case of inductor, the current cannot change through inductor instantaneously. The same like voltage across capacitor cannot change instantaneously. And as soon as the switch is closed in the network, the capacitor acts as short circuit. This we have seen from the basics. You can refer to the tabular column. Now capacitor acts as short circuit and at t equal to 0 plus, this is how the circuit will look like. Now you see switch is closed and capacitor is acting as short circuit. Now you can see 20 volts is supplying 12 ohms through current I of 0 plus. Therefore I of 0 plus will be equivalent to 28 divided by 12 because the circuit is closed. Naturally 28 by 12 will give you the value as 2.33 amperes and voltage across capacitor cannot change instantaneously. Moreover, the voltage for a short circuit is equal to 0. So in the practical circuit as well as in the field conditions, both are matching values of voltages. So voltage of 0 minus is equal to voltage of 0 plus, whereas the current has changed because now the circuit is closed. Before the circuit was open, now the circuit is closed. As the circuit is closed, we have to take 28 volts divided by 12 ohm resistance. So that's why we got the value of I of 0 plus as 2.33 amperes. This we need to keep in our mind and take this as equation 4. Now for time t greater than 0, the actual circuit when the parameters are connected to 28 volts. So I'm applying Kirchhoff's voltage law, that is assuming some of the voltage drops in a closed circuit is equal to 0. So you have minus 28 on this side plus 12i plus 1 by c integral idt. 1 by c integral idt is the value of voltage through capacitor. So 1 by c value is 10 millifarads integration idt equal to 0. Now differentiating equation 5 with respect to t, I am going to get this constant value as 0, 12 di by dt plus, you can see milli is there. Milli when you go to the numerator becomes 1000, denominator you have 10. So differentiation of integration it becomes I is equal to 0. I hope you understood this particular differentiation. Now simplifying this equation, I am going to get di by dt is equal to minus C10 100 times, so it is 100 I. So this 100 I on the left hand side goes as minus 100 I. Now you have di by dt multiplied with 12, so that's why here it is getting divided by 12. So minus 100 I by 12. This is the equation 6 we frame. Now at t equal to 0 plus, this I of 0 plus by dt will be equal the value as minus 100 by 12 multiplied with I of 0 plus. So I of 0 plus from equation 4 we got the value as 2.33 amperes. So we are going to substitute this equation 4 in equation 7. So we are going to get di 0 plus by dt is equal to minus 100 by 12 multiplied with 2.33. Now this value will be obtained as minus 19.416 ampere per second. I hope you understood this particular numerical, how we got the value of di of 0 plus by dt. Now again differentiating equation 6. Why need to differentiate equation 6? Because we require d square I by dt square. So d square I by dt square is equal to minus 100 by 12. This d I becomes di by dt. So we need to obtain at t equal to 0 plus. Just substitute the value. So it becomes minus 100 by 12. Multiply this I of 0 plus value, which is nothing but minus 19.416 amperes over here. We are going to get 161.8 amperes per second square. So this is how we solve the problem under RC circuit when the transient switch is applied across DC. Now we are going to take resistor, inductor, capacitor all in series connected through a switch through a supply source 48 volts. Now we know the property of inductor and property of capacitor, their initial conditions, their final conditions. So we are dealing with the initial conditions and we need to derive the same values of velocity current and acceleration of current. So when the switch is open, there is no current passing through the network. So at t equal to 0 minus, you have current as 0, voltage as 0. So both are before switching conditions. So equations 1 and 2 are treated like this. And we know that the inductor current cannot change instantaneously and voltage through capacitor cannot change instantaneously. So at t equal to 0 plus also, the behavior of the circuit which becomes open circuit for the inductor, short circuit for the capacitor. So you'll be having V of 0 plus is equal to 0, I of 0 plus is also equal to 0. So this is the important point we need to observe in the case of inductor and capacitor, the initial switching conditions. I hope you understood these four equations, how we have framed based upon the initial conditions, how the behavior of voltage and current through a closed circuit applied to DC, it will be giving you the values as 1, 2, 3, 4. Now with this, when the circuit is closed and after t equal to 0, when these parameters are supplied to DC, we are going to frame the transient equation, that is minus 48 plus 50 times I plus L di by dt. L plus we have 12, so 12 di by dt plus 1 by C integral I dt. So 1 by C value is 22 millifarads. So 22 millifarads integration I dt is equal to 0. So this is the equation what we can frame for transient current. Now at t equal to 0 plus, we need to obtain the di by dt of 0 plus value. So minus 48 plus 50 times I of 0 plus 12 d times I of 0 by dt plus 1 by 22.22 millifarads integration of I of 0 plus dt, which is equal to 0. Just we have substitute the value of I of 0 plus in the equation 5. And with this substitution, you can see minus 48, it will be as it is. 50 multiplied with 0 will be 0 plus 12 di by dt. So this I of 0 plus value plus 1 by 22.22 millifarads applied with 0 dt is equal to 0. So with this I am going to get 12 di of 0 plus by dt is equal to 48. So this value will be obtained as 4 amperes per second. I hope you understood this small simplification how we have made in order to obtain the value of I of 0 plus differentiation, whose value is 4 amperes per second. Now once we obtain the value of I of 0 plus under differentiation, that is the velocity value of current as 4 amperes per second, differentiating equation 5, we are going to get, see your differentiation of 48 which is 0, 50 di by dt plus 12 d square I by dt square plus, this is milli, it goes to the numerator, it becomes 1000 divided by 22.2 times I is equal to 0. Now just taking 12 d square I by dt square is equal to minus 50 di by dt minus 1000 divided by 22.22 will give you the value as minus 45 I. Now just substitute the value of di 0 plus by dt, whose value is 4 amperes per second, and I of 0 plus value is always 0 here for this circuit. So I'm substituting these values. So this equation 7 becomes in this fashion, and we know that I of 0 plus is 0 and di of 0 by dt at under the plus condition is 4 amperes per second. Substitute this equation 4 and 6 in equation 8. You're going to get d square I of 0 plus by dt square is equal to minus 50 by 12 multiplied with 4 amperes minus 45 multiplied with this equation 4 whose value is 0. So this will give you the value as minus 16.66 ampere per second square. So this is how we solve the passive elements connected to DC under switching action. And this particular class we're reading as class 2. And in the beginning of the class I told you in class 3 we'll be seeing the initial conditions of inductor and capacitor in parallel circuit, and the later classes the arrangement of series and parallel circuit under transient analysis. So I hope you like my video, share among your friends and subscribe to my channel, and please press the bell icon for the future notifications. Thank you.